To understand the diversity of Indian agriculture, हमें सबसे पहले उसकी फाउंडेशन को deconstruct करना होगा, the soil. देखो, soil is not merely dirt. It is a complex, living entity formed through centuries of geological and chemical processes. Simple है ना? When we look at the classification provided by agencies like ICAR and USDA, we are essentially looking at the biography of the soil. How it was born, which is genesis, what it is made of, that is composition, and where it resides. A crucial question arises here. सवाल ये है, is the soil found in a region born from the rocks beneath it, or was it brought there by a river? This distinction leads us to the two most dominant groups shown in the map, alluvial soils and black soils. Let us first analyze alluvial soil, which covers the vast majority of the Indo-Gangetic plains. This is a classic example of azonal soil. इसका मतलब, meaning it is not native to the place it is found. It is a transported soil. Think of the massive energy of the Indus, Ganga and Brahmaputra river systems cutting through the Himalayas, carrying tons of silt and depositing it in the plains. Because this soil is constantly being deposited, it has an immature profile, meaning it lacks distinct horizontal layers that older soils have. Within this, we see a dynamic contrast between Khadar and Bhangar. As the visual suggests, Khadar is the new alluvium found in the floodplain. It is renewed annually, fine-grained and highly fertile. In contrast, Bhangar is the old alluvium found on higher ground away from the river, often containing calcium carbonate nodules known as kankar. Right? On the other hand, we have black soil, also known as Regur or cotton soil. Unlike alluvial soil, this is zonal or in situ soil. It was formed right where it sits, primarily from the weathering of volcanic rocks, specifically basaltic lava of the Deccan Trap. Its most defining characteristic is its clay content, specifically Montmorillonite clay. Note कर लो इसको. This unique mineral gives the soil a mechanism of self-plowing. When wet, it swells and becomes sticky. When dry, it shrinks and develops deep cracks. These cracks, visible in the diagram, are vital because they allow atmospheric nitrogen and oxygen to penetrate deep into the soil, naturally aerating it. While it is chemically rich in iron and magnesium due to its basaltic parentage, it typically struggles with a deficiency in nitrogen and phosphorus, which is a common trait in Indian soils.
We have understood what soil is. अब हमें देखना है कि soil के साथ हो क्या रहा है. We are facing a crisis of land degradation, which is the persistent decline in the biological productivity of the land. According to the ISRO data presented, nearly 30% of India's total geographical area, or TGA, is undergoing degradation. This is not just about soil losing nutrients, it is about the structural collapse of the ecosystem. Serious baat hai ye. A key term here is desertification. It is a common misconception that desertification means the expansion of existing deserts. No, not exactly. In academic terms, desertification is land degradation occurring specifically in arid, semi-arid and dry subhumid areas. It is the land losing its life-sustaining capability. Let us analyze the causative factors shown in the sources of land degradation pie chart. The most dominant culprit is water erosion, accounting for the vast majority of damage. Within this, sheet erosion is often called the farmer's death. Why use such a fatalistic term? Kyunki sheet erosion removes the topmost fertile layer of soil evenly, like peeling skin. It is so subtle that it often goes unnoticed until the land becomes barren. This links directly to the vegetation degradation caused by deforestation and shifting cultivation, also known as jhum. When we remove the vegetation cover, we break the protective seal of the soil. The process flow diagram illustrates this vicious cycle of desertification. It starts with vegetation removal, which leads to soil exposure. Once exposed to the harsh sun and wind, the soil loses moisture and organic binding agents, leading to erosion and nutrient loss. This results in loss of productivity, which forces humans to overexploit the remaining land, further fueling the cycle. We must also recognize the anthropogenic drivers, human-induced factors. Overgrazing is a classic example of the tragedy of the commons, where shared pasture land is stripped bare. Additionally, in the Green Revolution belts, we see salinization and waterlogging due to the overuse of canal irrigation. When the water table rises too high, it chokes the root zone, turning fertile fields into saline wastelands.
To combat soil loss, हमें erosion की physics को समझना पड़ेगा. Specifically, erosion dynamics, which is how energy is transferred from wind and water to the soil particles. Erosion is not a singular event, it is a sequence. The water erosion sequence visual details this progression perfectly. It begins with splash erosion, where the kinetic energy of a falling raindrop bombards the bare soil, dislodging particles. This may seem minor, but it loosens the structure. सोचो जरा, एक single drop का impact. This is followed by sheet erosion, which we previously identified as the most dangerous for fertility because it washes away the nutrient-rich topsoil uniformly. If unchecked, water concentrates into small channels called rills, creating rill erosion. Over time, these rills deepen and widen to form gullies. When gully erosion becomes extreme, it leads to the formation of ravines or badland topography as seen in the Chambal Basin map. Here, the land is so cut up by deep gullies, some 15 to 30 meters deep, that it becomes impossible to farm or inhabit. This is a result of both natural neotectonic activities and anthropogenic deforestation. The soil here has lost all structural integrity. Parallel to wind, we have wind erosion, which follows a different set of aerodynamic mechanisms shown in the visual. Wind moves soil in three ways based on particle size. Listen carefully. The finest particles, dust, are lifted high into the air in suspension and carried for kilometers. Medium-sized particles cannot fly. Instead, they bounce along the ground in a process called saltation. This bouncing is destructive because every time a particle lands, it dislodges more soil, creating a chain reaction. Finally, the largest particles, too heavy to lift, simply roll along the surface in surface creep. This mechanism is responsible for the shifting of sand dunes and the abrasive damage to crops in arid regions. Understanding whether the erosion is driven by suspension, saltation or creep is critical for designing barriers like shelter belts. Clear hai?
Having diagnosed the disease of erosion, we now move to the cure: soil conservation strategies. Conservation is fundamentally about managing the velocity of water and wind. Logic simple hai. If we can slow down the flow, we reduce the erosive energy. We classify these measures into two broad categories: agronomic or biological and engineering or mechanical. Agronomic measures involve changing how we farm to use nature as a shield. Look at the integrated biological conservation visual. It depicts contour farming, where plowing is done across the slope rather than up and down. Each furrow acts as a mini dam, intercepting runoff water. Another effective biological technique is strip cropping. Here, we alternate strips of erosion-permitting crops like cereals, which have narrow leaves, with erosion-resisting crops like legumes, which have dense foliage. The legumes act as a buffer, trapping soil that washes away from the cereal strips. Samajh aaya? Mulching is another vital practice shown in the diagram. By covering the bare soil with crop residues or straw, we prevent direct evaporation and, more importantly, cushion the soil against the impact of splash erosion. For wind erosion, we use shelter belts, rows of trees planted perpendicular to the wind direction to break the wind's velocity. However, when the slope is steep or the erosion is severe, biological measures are insufficient. We need engineering measures. The slope versus terrace visual demonstrates terracing, where the slope is cut into steps. This transforms a rapid runoff surface into a series of flat platforms that hold water, allowing it to seep in rather than rush off. In areas with gully formation, we construct check dams. As shown in the cross-section, a check dam is a small barrier built across a gully. It serves two purposes. It reduces the velocity of water flow, preventing further cutting of the gully, and it causes sediment to settle behind the dam. This stagnant water then percolates down, recharging the groundwater table. Thus, conservation is not just about saving soil, it is about water management too.
Sometimes the soil is not physically lost, but chemically corrupted. This brings us to soil remediation and reclamation. We often categorize problematic soils into saline, alkaline, and acidic, but understanding the chemistry between them is crucial for treatment. Saline soils, often called white alkali due to the white crust of salts like NaCl and Na2SO4 on the surface, have a problem of excess soluble salts. The remediation here is physical, leaching. As shown in the matrix, we flush the soil with massive amounts of water to dissolve the salts and drain them away through subsurface drainage. Easy, right? However, alkaline or sodic soils, also known as black alkali, present a tougher chemical challenge. Here, the problem is not just salt, but exchangeable sodium attached to the clay particles. Sodium disperses clay, destroying soil structure and making it hard and impervious. You cannot simply wash it out because the sodium is chemically bonded. Listen to the solution. The chemistry in action visual explains the remedy. We add gypsum, which is calcium sulfate. The calcium, Ca2+, in gypsum is more reactive than sodium, Na+. It displaces the sodium from the clay particle. Think of it as a swap. The displaced sodium then reacts with sulfate to form sodium sulfate, which is a soluble salt that can finally be leached out. This is a classic ion exchange reaction. On the opposite end of the pH scale, we have acid soils, common in high rainfall regions like Kerala and northeast India, where bases are leached away. The indicator here is a pH below 6. To fix this, we need a base to neutralize the acidity. We use liming materials like calcium carbonate or dolomite. The acid soil management visual shows how lime adds basic ions to the soil, raising the pH to a neutral level suitable for farming. Beyond chemicals, we're moving towards bioremediation. This involves using phytoremediation, where specific hyperaccumulator plants are grown to suck up toxins from the soil. Alternatively, we can adapt to the problem by growing salt-tolerant crops like barley and cotton in saline lands, rather than fighting the soil chemistry. Bilkul clear hai?
Agriculture cannot sustain itself if we treat soil like an inert, distinct container for chemicals. We must manage it as a living system, which brings us to soil health management. In 2015, the government launched the Soil Health Card or SHC scheme. The objective was to stop farmers from flying blind. Before this, fertilizers were applied based on guesswork or habit. The SHC acts like a medical report for the soil. बिल्कुल डॉक्टर की रिपोर्ट की तरह. As shown in Visual 1, it measures 12 distinct parameters. Macronutrients like nitrogen, phosphorus, potassium, secondary nutrients like sulfur, micronutrients like zinc, iron, copper, etc., and physical parameters like pH and organic carbon. This card is renewed every 3 years to track changes in soil health. The urgency for this scheme stems from the fertilizer imbalance depicted in Visual 2. Ideally, the ratio of nitrogen, phosphorus and potassium or NPK usage should be 4:2:1. However, in states like Punjab and Haryana, the graph shows a distorted reality where nitrogen usage is skyrocketing in the actual scenario. This is largely due to the heavy subsidy on urea, leading to its abuse. Serious issue hai ye, serious. Excess urea not only causes nitrate pollution in groundwater, but also makes the soil acidic and kills beneficial microorganisms. To counter this, we must look at eco-friendly solutions. Nature has its own fertilizer factories, bio-fertilizers.
The visual of the root nodule zooms in on a symbiotic relationship where bacteria like rhizobium live in the roots of leguminous plants. They fix atmospheric nitrogen and convert it into a form the plant can use. This is a natural, cost-free alternative to urea. Similarly, mycorrhiza helps in mobilizing phosphorus. Another innovation is neem-coated urea. By coating urea with neem oil, we slow down the release of nitrogen, a process called nitrification inhibition. This ensures that the plant absorbs the nitrogen slowly over time rather than it being washed away instantly. It also prevents the diversion of subsidized agricultural urea to industries, ensuring it reaches the farmer. Simple and effective.
Finally, we must zoom out from the microscopic chemistry to the macroscopic land use planning. Not every piece of land is designed for agriculture, and forcing it to be so leads to disaster. The Land Capability Classification, or LCC, pyramid illustrates this hierarchy perfectly. The pyramid ranks land from Class 1 to Class 8. Class 1 land at the base is flat, fertile, and has no limitations, ideal for intensive agriculture. As we move up the pyramid to Class 4, limitations like slope and erosion risk increase. By the time we reach Class 5 through 8, the land is non-arable. As the label indicates, this land is fit only for forestry, wildlife, or recreation. Farming on Class 8 land, like steep cliffs, is not just unproductive, it is ecologically criminal. To manage these diverse landscapes effectively, we adopt integrated watershed management. A watershed is a hydrological unit, an area where all water drains to a common outlet. Instead of treating a farm in isolation, we treat the entire catchment area. If we conserve soil and water at the ridge or top, the valley or bottom automatically benefits. This holistic approach combines soil conservation, water harvesting, and livelihood generation, which is the core of the Pradhan Mantri Krishi Sinchai Yojana. On a global scale, India is committed to fighting land degradation. The Global Commitments graphic highlights the UNCCD, the United Nations Convention to Combat Desertification, which is the sole legally binding international agreement on this issue. A key target here is SDG 15.3, which aims for land degradation neutrality, or LDN, by 2030. LDN means that the amount of healthy land we restore should equal or exceed the amount of land being degraded. India has pledged under the Bond Challenge to restore 26 million hectares of degraded land by 2030. Achieving this requires a triad of strategies shown in the icons: afforestation to hold the soil, reclamation to fix chemical imbalances, and sustainable agriculture to prevent future damage. This transition from exploitation to restoration is the only path forward. Got it?